Okay, so welcome back to this next video in which we are discussing the remainder theorem. Okay, so in the previous video what we discussed is what the remainder theorem actually says. Okay, and remember it says that if you take a polynomial, okay, which we'll call p of x, which has coefficients in the complex numbers, okay, and you then pick an arbitrary complex number alpha, okay, then what you can do is you can factor out this linear term x minus alpha from your polynomial. Okay, so you can rewrite your polynomial as x minus alpha times some quotient q of x, okay, and this is a polynomial of degree n minus 1, where n is the degree of the original polynomial, plus some constant term, okay, which is called the remainder term, okay, and this will just be a complex number, and we can actually say exactly what that remainder will be equal to. It will equal the polynomial evaluated at alpha. Okay, right. Now, this has a very special form when this alpha that you pick is actually a root of the polynomial or a zero of the polynomial. Okay, so if you just happen to pick an alpha which is the root of the polynomial or the zero of the polynomial, then what that means is that p of alpha is equal to 0. Okay, now that then means that the remainder term here is going to be equal to 0, okay, and that means that you can factor out x minus alpha, okay, this linear term x minus the 0 of the polynomial from the polynomial, okay, and that's going to have big consequences. We can combine this with the fundamental theorem of algebra to get a very nice result, basically. Okay, so let's do that now. Okay, right, so let me just tell you what the fundamental theorem of algebra is. Now, we're not going to actually prove this. It requires, at the very least, some complicated concepts from analysis to prove it, okay? There are many different ways of proving it. The simplest ones require some quite complicated concepts from analysis, namely the idea of compactness, okay? So we're not going to prove the fundamental theorem of algebra. I'm just going to state what it is, okay? So it's often abbreviated down to FTA, for fundamental theorem of algebra, okay? And it's called that for old historic reasons, okay? It's not really a fundamental theorem of algebra at all, okay? It's a fundamental theorem about the complex numbers, so it's a fundamental theorem in classical algebra, because classical algebra is all about the complex numbers, okay? But there are different theorems that have better claims probably to be called the fundamental theorem of algebra, but it's given that grandiose title for historic reasons. Okay, right, so what does the fundamental theorem of algebra says? What does the fundamental theorem of algebra say? Okay, so the fundamental theorem of algebra says that if you have a polynomial, let's say p of x, which is some polynomial with coefficients from the complex numbers, so let me just write it out here, Pn x to the power of n plus Pn minus 1 x to the power of n minus 1 plus all the way down to p0, okay, and again the degree of the polynomial needs to be greater than or equal to 1, okay, so we're not talking about just constant polynomials or even worse the 0 polynomial, okay, we are talking about polynomials which actually have the x indeterminant in them. Okay, so if you have a polynomial which has degree greater than or equal to 1, then basically this absolutely always has a solution within the complex numbers. It has a 0 in the complex numbers. So there exists, this backwards e means there exists a complex number, let's say alpha, which is an element of the complex numbers, such that when you evaluate the polynomial at alpha, so when you insert alpha in for x here, it gives you 0 basically. There always exists some complex number such that when the polynomial is evaluated at that complex number, the answer is going to be 0 basically. That is what the fundamental theorem of algebra says. It says that any polynomial with coefficients over the complex numbers will always, absolutely always, have a 0 within the complex numbers basically. Okay, right. So, what we are now going to do is we're going to combine the fundamental theorem of algebra with the remainder theorem to then show that actually this means that a polynomial of degree little n, so our polynomial here has degree little n, will actually have little n zeros basically, and that you can factorize your polynomial out into a multiplication of all of these linear terms, x minus alpha, okay, where the alphas are solutions to the polynomial, roots of the polynomial, zeros of the polynomial. Okay, so let's do this then. Okay, right. So let's start off with our polynomial here. Okay. So what we can do is apply the fundamental theorem of algebra and say within the complex numbers there will be a complex number alpha which satisfies this polynomial, and then what we can do is we can use the remainder theorem to say that we can therefore write the polynomial as this x minus alpha, so where alpha is now this root of this polynomial, times some quotient q of x. And I've said that when we pick alpha very cleverly so that it is a root of the polynomial, then the remainder term will be 0 basically, so it factors perfectly. So what we can now do then is we can rewrite our polynomial p of x as x minus alpha times some new polynomial q of x, which will have degree n minus 1 basically. Then what we can say is this new polynomial q of x, we can apply the fundamental theorem of algebra again. Okay, and we can say that there will be some new complex number, which, well, potentially new, it might be exactly the same one, okay, but we can say that there is some complex number which will be the root of that polynomial, i.e. when you evaluate q at that complex number, it will give you 0. Okay, let's call this new complex number alpha 2. So in fact, let's say that this one can be alpha 1. We'll call the first root that we got alpha 1. Now we're going to apply the fundamental theorem of algebra to q of x, and we'll say, okay, we'll call this root that must exist for q of x now, okay, because q of x is just a polynomial as well, so we can apply the fundamental theorem of algebra and say that there must be some alpha 2 which is in the complex numbers such that q of alpha 2 is equal to 0. Okay, then what we can do is we can rewrite now q in terms of x minus alpha 2 times some other quotient basically. Okay, and I'm running out of symbols, so I'll call this one now q1 just as I called this one alpha 1. Okay, and I'll write now q1 of x as x minus alpha 2 times q2 of x. So q2 of x is now some new quotient. Okay, it will now have degree n minus 2, so q1 had degree n minus 1, p had degree n. Okay, we're gradually going down the degree, so this quotient now over here will have degree n minus 2 basically. Okay, and what we can now just do is substitute in q1 of x is equal to x minus alpha 2, q2 of x, and then what we'll get is that polynomial p of x is equal to x minus alpha 1 times x minus alpha 2 times this q2 of x, which now has degree 2 less than the degree of the original polynomial p of x here. Okay, and we can continue this process on and on it can go basically. Okay, and eventually what we will do is we will reduce it down to the point where we have x minus alpha 1 times x minus alpha 2 all the way down to x minus alpha n. So this will continue on all the way down until we get x minus alpha n, and then what we'll be left with right at the end is some constant term. So I'll put this out here. We'll end up with beta, let's say. Okay, and beta will be what's left over when we get right down to a polynomial, okay, a quotient polynomial here, which is a linear polynomial. Okay, so it's a degree 1 polynomial, and that degree 1 polynomial, if I just write it out, it might be, let's say, ax plus some b. Okay, and obviously when we factorize out x minus alpha n, we will then end up with this constant term here. Okay, so that will end up being pulled out basically. Okay, the reason that that has to be there is if you imagine reducing the polynomial down to x minus alpha 1 times x minus alpha 2 all the way down to x minus alpha n, and it's perfectly done here. Okay, then you can see that the highest degree term, which is just where you multiply all of the x's out, could only ever have coefficient 1. So we couldn't possibly get it to have this general term here. So in fact, that constant term there must equal the constant term out the front here, basically. Okay, so that you can get a non-1 coefficient of this x to the power of n term, basically. Okay, right. So what this then means is that we can write our polynomial p of x as some constant term multiplied by x minus alpha 1, x minus alpha 2, all the way along to x minus alpha n, where alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, all the way up to alpha n are all zeros of this polynomial, basically. We can rewrite our polynomial in this form. So that proves now that this polynomial p of x has little n zeros, basically. All of these are zeros. Now, they're not necessarily distinct. Some of these might be the same complex number, okay, but we will still count them as zeros, basically. We'll still count them as zeros of the polynomial, and you factorize your polynomial out into these multiples of x minus a 0, basically. Okay, right. The final thing then to say is that the polynomial doesn't have any other roots besides these ones that we found, basically. Okay, and the easy way of seeing that is that suppose it had some other roots, let's call it gamma, okay, which wasn't any of these ones here, okay, then basically if I put gamma into the polynomial, if I work out what is p of gamma, I'm saying that gamma goes into this polynomial to give 0, but I want to show that that's not possible, basically, because I can rewrite my polynomial here like so. Okay, so if I want to work out what p of gamma is equal to, I can just substitute it in here. So I'll get gamma minus a1, or rather alpha 1, gamma minus alpha 2, all the way down to gamma minus alpha n, okay, times beta here. Okay, now why can this not possibly equal 0? Well, if gamma is not equal to any one of these little m roots here, then none of these terms here are going to be 0, basically. Okay, so I'll say that again. If gamma is not one of the roots that I've got in my factorization here, then none of these linear terms here are actually going to equal 0, okay, because they'll only equal 0 when you put in one of the answers, basically. So if I put in alpha 1, then this first one would be equal to 0, but if gamma is not equal to any of these roots, then none of these linear multiples will equal 0. So I'm multiplying together loads of things that are not equal to 0. I cannot then possibly end up getting 0 out. You cannot multiply two non-zero complex numbers together and end up with 0. That's not doable, basically. Okay, you can add two non-zero complex numbers together and get 0, but you can't multiply them together and get 0. Okay, the only way to multiply two complex numbers together and get 0 is if one of them is 0. Okay, so if I'm multiplying together loads of non-zero complex numbers, whatever I get, it's not going to be equal to 0, which proves that gamma cannot possibly be a 0 of this polynomial unless it is one of the zeros that I've already found, basically. So that then proves that this polynomial p of x has little n, its degree, number of zeros, and no more, basically. Okay, and I'll stress again that they're not necessarily distinct, but they will be distinct linear terms in this factorization, basically. Okay, so you might have repeated linear terms, but it's important to note that the polynomial requires that term to be repeated, basically, if the 0 is repeated. Okay. Right, okay, so that's how, with the fundamental theorem of algebra, which we haven't proved, it's quite a hefty proof, but with the fundamental theorem of algebra and the remainder theorem, we can then derive this result that every polynomial with coefficients in the complex numbers has little n, its degree, number of zeros, okay, and it can be factorized into these linear terms which are x minus one of its zeros, okay. Right, so that concludes our discussion of the remainder theorem.